So this old laptop has something that modern PCs don't have today, and it's this 9-pin D-shaped connector, and it was referred to as a COM port or an RS-232 port or as a serial port, and that's how you connected peripheral devices to your PC to control them or download data from them. Or in the case of my hobby, another hobby I have is amateur radio. It's how I program my radios, is through a serial port. But and that was also a convenient way to hook up your microcontroller projects to a PC to be able to see the output from whatever the microcontroller is doing. But sadly, today, these COM ports are being replaced by these ports here, the USB ports. And to write software to implement the USB protocol on a microcontroller is really difficult. And depending on what you're doing, you might even need a license to do it. But luckily, today there are devices like this guy, specifically the chip that's in the middle here, which are USB to serial converter chips. And it enables you to plug this into your PC and the other end of it into your microcontroller and communicate over the USB port. Now, if you remember my DDS project that the last video I was doing with the DDS, the Direct Digital Synthesis project that I was working on, and I was controlling the frequency that it was outputting by typing the frequency on my computer. Well, I was using something like this in order to talk to my PC, because I have a modern PC and it doesn't have that COM port anymore, only the USB ports. So what I'm going to do is show you how to use the serial port in the microcontroller, the ATmega328, how to hook it up to this end here, and then you simply just plug the other end in, of course, into your PC, and it's already set up and functional. You don't have to do anything about it. But I will show you how to send data down the serial port. If you were to look up RS-232 on the internet, you'll find that Wikipedia has a good article on it. And the RS-232 standard defines the electrical characteristics of the signals, but not the timing. And there are quite a number of signals under the RS-232 standard, such as RX, TX, DTR, CTS, RTS. There's, how many are there? Must be a dozen or more, many of which aren't used today. It also defines the connectors that are used as a part of the standard. The original one was a DB25, which is a 25-pin D-shaped connector. You saw the DE9 connector on my laptop. That's a newer standard, and there's a lot less pins, obviously, because a lot of these signals aren't really necessary anymore, especially with high-speed microcontrollers. So the minimum number of signals that you need to communicate between two devices, in this case a microcontroller and your PC, are the RX, the TX, and ground. And RX is just the data received by whatever device it is, and it's the same name whether you're talking about the PC or the microcontroller, for example. TX is the data transmitted by a device, so that's the data leaving the device. RX is the data coming into the device. And then the electrical ground, just so there's a reference between the two devices. And those are the only signals that you actually need to make a microcontroller communicate to a PC. And they hook up like this. And because they have the same definition on either side, you have to cross them over. So the RX from the PC goes to the TX of the microcontroller, and vice versa. The ground, of course, is connected straight through. Now, if you're familiar with any of the other serial standards like SPI and I2C, and stay tuned, I will have videos on those as well. But for now, I'm just going to talk about a few things that you may not understand. But with this RS-232 standard, you can only connect two devices together. That's point to point. No multi-drop, which means that there's no way you can have a single master and a bunch of slaves connected up to the same data bus and communicate that way. Those other two standards I mentioned allow that, but we're not going to talk about those at this point. The advantage of this method here is you can have simultaneous transmit and receive at the same time. So the PC could be transmitting data to the ATmega328 while it's transmitting data back to the PC. There's limitations within the microcontroller here and just how powerful it is to be able to receive and transmit at the same time, but technically you can do that, and it's called full duplex operation. Now the RS-232 standard provided for some clocks to time the data bits being sent out, and so there were two separate clocks, a transmit clock and a receive clock, but they're not used, and I don't think they ever were used much, even at the heyday of the RS-232 standard. And the way it's done now is that the clock rate is implied. That is, the bits are sent out at a certain timing, and both sides, the transmitter and the receiver, have to agree on the same bit rate in order to communicate. You might also have heard the term baud rate. It means the same thing. A very common bit rate used back in the day, and this is my memory because I was using computers and mainframes in the past, was 9600 bits per second, which was fast enough that anybody typing even really quickly would not be faster than 9600 bits per second. Other typical baud rates or bit rates is 19,200 or 38,400. You can't go a whole lot higher than this because the timing becomes very critical, and any kind of distance that you have to transmit that data, the bits get kind of trashed by the noise and other problems with the cabling, and you just can't transmit data at that speed. And that was one of the reasons why USB was developed, is it can transmit data at much higher speeds. Now, how do we know how to transmit data? How do you know when somebody's beginning to transmit data on the line? Well, normally when there's no data on the line, it's idling. And so this is from the perspective of a microcontroller now, so all the bits are in the positive direction. So a 1 bit is a high voltage and a 0 bit's a low voltage. And that's how I'm going to talk about it for the rest of this video. The RS-232 standard is not used with the microcontrollers. But how do you know when you're starting to transmit some data? Well, the data line, the transmit line, idles high. And then the first thing that happens is a start bit is sent, which is a low. And it stays low for the appropriate bit time. And did I put it down there? Yeah. So going back to the 9600 bits per second, that's what I'm most familiar with, because that's what I did most of my work with, was at this bit rate. It works out to about 104 microseconds per bit. So whoever was transmitting would bring the transmit line low for 104 microseconds before starting to transmit the data. In this example, I've transmitted 8 bits, or 1 byte, and I've transmitted hexadecimal 35, which is equivalent to the ASCII character 5. So if you type the 5 on your keyboard, this is how the data would get transmitted for that 5. And it transmits the least significant bit first. So it would be the lowest bit here, or the 1 bit for the 5 part of the character. So actually, I think I've done this incorrectly. Oh no, I've done it wrong. No, this is correct. Anyways, let's keep going. So 8 bits of data coming out, 10, 10, 10, and each of these are 104 microseconds long. And you can see here there are 2 1-bits side by side, so the line just stays high for twice the 104, 208 microseconds. And same with the low here. If you write out this ASCII 3.5, it would be, well, I'll let you do that as a homework exercise, but this is how it gets transmitted out. After the most significant bit is transmitted, the high order bit, which would be the 0 bit of the 3, a stop bit is issued, and the stop bit is held for also 1 bit time, 104 microseconds, and then the line is considered idle. If the next character is going to be transmitted, it cannot be started here. You have to wait this 1 stop bit, and then the line gets pulled low again for the next start bit for the next character. So that's essentially how data is sent down the line. Now, this whole thing here, from start bit to the end of the stop bit, is called a frame. Now, the standard types of communications, not RS-232, because RS-232 does not define the number of bits or the start bits or the stop bits. But there are other standards that defined the number of start bits, the number of stop bits, the number of data bits. And so the common ones were there was always one start bit, never any more than that. You could transmit 5, 6, 7, or 8 or 9 data bits in your frame, and sometimes another bit was appended. They called that the parity. And then you could transmit at least one stop bit or 2 stop bits. To explain what parity is, it's just a method of error correction or error detection. And what it does is just counts the number of 1 bits in a frame, and then it appends another bit to make sure that the number of 1 bits is either odd or even. So in this case, if it was even parity being transmitted, I would append another bit after the most significant bit here, where the stop bit is now, and that bit would be either a 1 or a 0 depending on the number of 1s in this one, in this frame here. And in the case of, say, an even parity, I would count up the 1s in the data. So 1, 2, 3, 4, that's an even number of 1s, so I would append a 0 in the parity bit location. If I had odd parity defined, I would count at 1, 2, 3, 4. Well, that's even, so I need to transmit an odd number of 1 bits, so the parity bit would become a 1. So the total number of bits in there would be odd. That's how parity works. We don't use that anymore. So our standard today that everybody uses is 1 start bit, 8 data bits, no parity, and 1 stop bit. And it's often written out as, can you see that? Nope. Pull it up a bit. It's often written out as 8N1, as you can see here. So the next thing we're going to look at is how this is implemented in the microcontroller.
Let's have a look at the ATmega 328 datasheet. Now, when you're talking about serial ports, you often hear the term UART, U-A-R-T, which is an acronym. It stands for Universal Asynchronous Receiver Transmitter. In the ATmega, Atmel calls it the USART, Universal Synchronous Asynchronous Receiver Transmitter, because it gets used for another type of serial port where it is synchronous. Synchronous means that there's an external clock signal that coordinates the transfer of the data. In the case of the COM port, the serial port that we're going to do here, there is no external clock line. The clock is implied in the data itself. So if we open this up and let's look at the block diagram for it. So this looks rather complicated, but it isn't really too bad. There are 3 sections to it: the clock generator, the transmitter, and the receiver. And these are the I/O pins that it associates with. In our case, with its asynchronous, we're not going to be using the clock pin, but we will be using the transmit and the receive pins. Now, the main thing about this is you have to generate a clock internally. Whether you're synchronously or asynchronously transmitting data, you still have to generate a clock. And there's a register that you write to that gets used to divide down the main oscillator of the microcontroller to generate the clock signals. We'll talk about that in a moment here. Now, in the transmitter and the receiver, there's a register called a transmit shift register or a receive shift register. Shift register is the key part. And what they are is that you can download, or you can load into that shift register. It's 8 bits wide. You can load into that register 8 bits at once in parallel. And then with the clocking generated by the clock generator here, it sends out 1 bit at a time, eventually making its way to the transmit pin. And that's how you get the data out. This is a special kind of register that you can load it parallelly, and then you can shift out data 1 bit at a time. And how fast the bits are shifted out is depending on the clock rate. And the same with the receive register here. It's another shift register. And I'll have to go into more detail how it actually works, but it works in the same way, except it shifts the data in. It receives the data from the pin, it comes into one end of the register, and every clock pulse it shifts in another bit until you get 8 of them, and then it gets parallel shifted out, and then it can be read on the data bus. So let's first look at how to generate the baud rate, the clock generator. So this is a very simple block diagram of the clock generator circuitry. This part of it here we're not going to worry about because this is what generates the clock on a pin or receives a clock signal from another source for the synchronous operation. We're not going to use that. We're going to use the asynchronous operation here. So here's the baud rate register again, which is a register that you write to under software control, and that determines what your baud rate is going to be. And it simply is this number is divided into the clock frequency. So f-osc, the main oscillator frequency, 16 megahertz in the case of an Arduino, divided by this register. And you get out of here a frequency. Now, you can see that this frequency here goes down 2 different paths. One path goes through these dividers. These are divide by 2, divide by 4, divide by 2. And then ends out on the transmit clock. And that controls the shift register in the transmitter. Now the other path, it goes directly out without any dividers to the receive clock, which controls the receive shift register. Why would the clock, or the receive clock, be faster than the transmit clock? Well, I'll show you that in a moment. So for the transmit clock, it gets divided by 2 and then divided by 4 again before it has a choice of either being divided by 8 coming out of this line and out to the transmit clock shift register, or divided by 16. And that's important. We'll talk about that in a moment as well. Now let's look at the receive register and how the data is received. So we look at this chapter, asynchronous data reception. So if we look at this as being the received data from the pin, and it goes low for the start bit, and then after the start bit you've got all the other bits going on here. So what the circuitry in the microcontroller does is it detects this falling edge of a start bit, and then with the 8 times or 16 times clock, which remember it's faster, the clock rate is faster for the receive than it is for transmit, it samples. Every one of these arrows is a sample all the way across. So if it's 16 times, it'll sample 16 times during this start bit. If it's 8 times, it'll sample 8 times. And what it does is it looks at the middle 3 samples, either the 16 times or the 8 times, and it's a majority vote. If 2 or more of these samples read the same, then that's the value that it will take. And so in the case of a start bit, you want to see all of these, or at least 2 of these, being 0 for the receive circuitry to detect the start bit. Now the same with these 3 samples of the 8 times sampling. And if we look at the rest of the data bits coming in, it's done the same way. So each one of the data bits comes in is sampled 8 or 16 times, and then the middle 3 samples are looked at to determine whether it's a 1 or a 0. So that's how the receiver works, and why the receive clock rate is much faster than the transmit rate. So this is the data register, and this is actually the shift register, or at least it has access to the shift register. And so you write your data to be transmitted into here, or you read from this register the data that you've received. And that's called UDR0. And in the software, you will use this as a label, and it's already defined for you, and I'll show you in the software how to work with it. The next register is the control status register A, and these just tell you what's going on. So the first bit here, RX complete, just tells you when there's a byte in the receive register fully received and correctly received. There was no errors. And that bit will get set when that's the case. And then when you read from that data register, the one we just looked at, this bit will automatically get cleared. Same with the transmit register, but this is just a bit opposite. When the transmit register is empty, or the transmit is complete, then this bit gets set. And when you, let's see, I don't know if this is automatically, yeah. Oh, you just have to clear this one manually by writing to it. This isn't a bit that I normally use, actually. It's just the one I use here. This indicates that the data register is empty, meaning that there's not the data has been transmitted and the data register is empty, so this bit will be set high, and it tells you that it's ready for another byte to be sent out. And when you write to this, write to the data register, this flag will automatically get cleared. Now these next 3 bits here are just error bits, and you can only read them. You clear them. Oh, I guess some of them these are cleared when you read the data register. So the first one is a frame error. The next one is data overrun. I believe the frame error means that it didn't get a stop bit at the right time. It was expecting a stop bit and it got a 0 instead of a 1. The next one is a data overrun, meaning that the data came in, the received data came in too fast and you weren't reading it fast enough, or your microcontroller, your program wasn't reading it fast enough, and it's a data run error. And then this one is a parity error, and we're not going to use parity in any of the stuff that we're doing here, but if there was something wrong with the data that came in and it didn't match the parity that you'd set up, this bit would be set to 1. This is the bit that I was telling you about, the double speed. Let's have a look quickly here again. Clock generation. So you can see this is the bit here, UTX, U2X. U2X. So this just determines whether you're sampling 16 times or 8 times during the receive. Bit 0, ignore it, we're not going to use it. Next, register. So this is where we turn the receiver and transmitter on, and this is also where we enable our interrupts. So we have 3 different types of interrupts. We can have an interrupt generated when the receive is complete, so that's when a byte is fully received in the receive register, or when the transmit register becomes empty, it'll set an interrupt. Or actually when the transmit's complete, or when the data register is empty, you'll get an interrupt as well. And these bits, when set, will enable the interrupt. And I'm not going to talk much about interrupts for this because the code that I'm going to show you does not use interrupts. These 2 bits simply turn on the receiver and the transmitter. You set them high to turn them on. These bits here, the next few, set the character size. So there's 2 bits here. Oh, sorry, this is an extended bit because we are in another register for the other 2 bits. We'll come back to this one in a bit. This here would be the bit, if you were actually receiving and transmitting 9 data bits instead of 8, this is where that extra bit would show up. Again, don't worry about it, we're not going to use it. Same with the transmit data bit. If you're going to transmit 9 bits, this is where the extra bit will be. The next register, so these are the UART's mode setting registers, or setting bits, and there's 4 states: asynchronous, synchronous, and then master SPI. We're not using any of these 3 here, we're just going to use this one here, so these bits are going to be 0. The parity, these 2 bits here set the parity, and again we're not going to use them, but it'll always be 0 because we're not using parity. But then you can also set odd or even parity. The next, where we are, USB 0, oh yeah, this is the stop bits. The number of stop bits. So if it's 0, we've got 1 stop bit. So here it is here. 0 is 1 stop bit, and a 1 is 2 stop bits. We're not using 2 stop bits, we're only using 1. And now the character size is the next 3. Well, actually, these 2 bits here in this register, and in this 1 bit here in the other status register. So they're combining 2 status registers to get our the number of bits in our word And we are normally going to be doing it 8 bits, and I believe this is how it resets to. Let's just have a look here. Yes. So this is the reset value. So upon a power on reset or a software reset, these are what the bits will be in this register after the reset. So in this case, it's setting these two as 1, and the other bit in the other register, let's go back to it, which is, wrong one, I was right. This one here, this will be 0, so that's the upper bit of that register, of these 3 bits that they're using. So this is the upper bit, which is in the status register B, and we're just looking at these two here. So we notice that these 2 bits in status register C are set on reset, so it automatically defaults to 8-bit, so we don't have to do anything with those. And the rest of these deal with the synchronous modes, and we're not going to worry about them. So that's the 3 status and control registers that you need to set up, and I'll show you how to do it in the software as well in order to get the UART to work the way you want it to work. It's pretty simple. It looks complicated. You got 3 registers to deal with, but it really isn't that difficult to work with, because in our case here, it's going to come up in the mode that we want anyway, so we won't have to really manipulate things too much. The one thing that we will have to manipulate are the 2 baud rate registers, and it's a 16, actually no, it's not, it's a 12-bit register. So you have to write a low byte and an upper byte. And again, I'll show you in the software how to do that.